Imagine a shop where every item's final price depends on a future item's price. How do you efficiently calculate these discounted prices across an entire inventory? This problem challenges us to find that exact discount. Given an array of prices, for each item I, we need to find the first item j that appears after I such that its prices, j, is less than or equal to prices, I. If such an item j exists, the final price for item I will be prices, j. Otherwise, the item I is sold at its original price. The task is to return an array of these final prices. A straightforward approach involves a nested loop. For each price at index I, we iterate through all subsequent prices starting from I+1 to find the first one that's less than or equal to prices, I. If found, we apply the discount and move to the next I. If the inner loop completes without finding such a discount, the original price is kept. This method works, but the inner loop for every outer loop iteration leads to a quadratic time complexity, O(n squared), because we're repeatedly scanning portions of the array. Space complexity is big O of 1, constant time if we modify in place, or big O of n for a new result array. The key insight here is recognizing a next smaller element pattern, which is often solvable with a monotonic stack. We can process the prices from right to left. As we iterate backwards, we maintain a stack of prices that are in increasing order. When considering prices, I, we pop elements from the top of the stack that are greater than prices, I. These popped elements cannot be the next smaller element for prices, I, or any element to its left. After popping, if the stack is not empty, the top element is the next smaller or equal element to prices, I, and we use it for the discount. If the stack is empty, there's no such element, so prices, I, remains unchanged. Finally, we push prices, I, onto the stack, ensuring its monotonic property. Let's trace this with prices, 8, 4, 6, 2, 3. We'll iterate from right to left. Starting with 3, stack is empty. Result at this position is 3. Push 3. Next, 2, stack has 3. 3 is greater than 2, so pop 3. Stack is empty. Result is 2. Push 2. Next, 6, stack has 2. 2 is less than 6. Result is 6 minus 2, which is 4. Push 6. Next, 4, stack has 6, 2. 6 is greater than 4, pop 6. Stack has 2. 2 is less than 4. Result is 4 minus 2, which is 2. Push 4. Finally, 8, stack has 4, 2. 4 is greater than 8, pop 4. Stack has 2. 2 is less than 8. Result is 8 minus 2, which is 6. Push 8. After processing all elements, our result array will be 6, 2, 4, 2, 3. Each element is either its original price or discounted by the first subsequent price that is less than or equal to it. You'll spot this next smaller element pattern whenever a problem asks you to find the first element to the left or right that satisfies a certain comparison, like being greater or smaller. This often signals a monotonic stack solution. The time complexity is big O of n because each element is pushed and popped from the stack at most once. The space complexity is also big O of n in the worst case for the stack. Mastering the monotonic stack is crucial for optimizing many array problems. Try the next problem to solidify this pattern. Don't forget to like and subscribe for more DSA insights.